because we kind of liked it when they gave us the double integral, because then it was just mechanical. You get right to work. I gave the figure here. It definitely looks a lot nicer on the big screen than it does on your paper. It's like a big gray blob. But what we're talking about is like a little capsule contained in it. So we have two different paraboloids intersecting one another. And the intersection forms a bounded region. That's what we're looking for. Right? So what I first would want to do is find the intersection of those surfaces. All right, very easy to do because they're both solved for y in terms of x, solved for z in terms of x and y. So we have x squared plus y squared is equal to 5 minus x squared minus y squared. We can add x squared and y squared to both sides. So 2x squared plus 2y squared is equal to 5. X squared plus y squared would be equal to 5 over 2. All right, so that's a circle, which, you know, like I said, the diagram on your papers aren't much to look at, but in this one here, if we're talking about the intersection, we're talking about the little area here. It could be a circle. All right, in that middle region there. All right, we're just talking about the border created by the intersection. All right. Now, in polar form, that would correspond to r equals the square root of 5 over 2. All right, because, I mean, you could do your substitutions. You can let x squared plus y squared equal to r squared, and then square root both sides. But the bottom line is you're really just finding the radius of your circle, and that ends up being your polar equation. So why not just cut to the chase? All right, so we have that. Our theta value, you know, if I did an xy trace of this, undo, you know, just based off of the diagram there, you know, no matter where I draw my circle, if I draw my circle down here, or up here, or up here, or down here, or down here, no matter where I draw my circle, it's still going to be a circle. And a circle goes from 0 to 2 pi radians. All right, so we have our r and we have our theta. Now we just need some way of representing the function. All right. So just like you would if you were finding the area between two curves, you find the area of the top minus the area of the bottom. I'm sorry, that's what you're looking for. You find the difference between the top function and the bottom function, which gives you the area bounded in between. Right? Because you know that you're integrating all of those little rectangles that go from the beginning to the end of the region. You just need the distance between those two functions. All right, so what you want to do here is find the top function, the top surface, and then subtract from it the bottom surface. So I need this guy. All right, so you got two choices. You got z equals x squared plus y squared. I'll write them both down here. And you have z equals 5 minus x squared minus y squared. All right. Now, if you made an educated guess without investigating any further, you'd probably guess correctly. If you're guessing that the function that's facing downward is the 5 minus x squared minus y squared, it's a good guess. It's the right guess. Right? Because you're starting off with something that has a value of 5 and you're only subtracting from it. Right? So that would mean that it has to max out when x and y are both 0 with a value of 5, because that would be the case where you're not subtracting anything from it, which would put it right on the z-axis, which is what's happening here. Right? But maybe you don't see it that way. All right. So if that's the case, one of my buzz phrases, I guess, you might say 5 minus x squared plus y squared in parentheses is the same as 5 minus r squared. All right. So what that's doing is it's creating a relationship between z and r. So as the radius increases, the z value gets smaller and smaller. All right. Or that's the equation of a parabola with a negative coefficient, which means it's opening downward. Right? So if you like that, you know, go right on back to algebra 1. You're like, oh, it's a downward facing parabola because the leading coefficient's negative. Right? The other one would be an upward facing parabola because z would be equal to r squared. All right, but if you can try to conceptualize this, it makes a big difference because what this is saying, again, is, you know, the r represents the radius, the distance away from the z-axis. As the distance away from the z-axis, as the radius increases, the figure gets moved further and further down the z-axis. All right, so that should naturally create that paraboloid look. All right, and this is the same idea, just in the opposite direction. All right, as the radius increases, it gets further and further up the z-axis. So that's a parabola going in the positive direction. All right, so if you start to try to internalize it that way, it definitely makes more sense. All right, so my double integral going from 0 to 2 pi, then 0 to root 5 over 2 of 5 minus r squared minus r squared, all that times r dr d theta. All right, so then we can clean it up. All right, so this component here, 5 minus 2r squared times r, which in turn becomes 5r minus 2r cubed dr d theta. I like that a lot better because it's just reverse power rule. That's nothing. Increase the power by 1. Divide by the new exponent. Increase the power by 1. Divide by the new exponent. All right, so this is going from 0 to root 5 over 2. So that's nice. We have even powers. That's the best thing that could happen when you have a square root that you're putting in. So 5 halves times 5 halves minus 1 half times root 5 over 2 squared becomes 5 halves, squared again becomes 25 over 4. Bottom line is, it's not radical anymore, so that's a win. So we're talking 25 over 8, 25 over 4 minus 25 over 8. Which is 25 over 8. So then I'm just dealing with a single integral going from 0 to 2 pi of 25 over 8 d theta. Well, that's just 25 theta over 8 on the interval of 0 to 2 pi. And so that's going to be 50 pi over 8, which would then be 25 pi over 4. I didn't really look at the calculator for this one because the numbers were just working out so nicely that it wasn't even worth getting into. Right? But it gets pretty messy. Well, I made it pretty messy because I made this so huge that I robbed myself of space elsewhere. But it's really not that bad compared to the other. And again, once you get to this step here, because really this is all, now honestly, because this is a function of one variable, this is all calculator if you want it, right? Because you could integrate this because there's no thetas in it. You could integrate this in your calculator, get the answer, and then integrate the result in your calculator. All right, so there's really, once you get the setup, there's really not many ways to screw this up. All right, but I have faith in you. You'll find a way. That was a joke. It was a bad one. All right, we're not finding anything funny tonight. Okay, cool. So I'm going to put a star on the next one. And then we will carry on to the next page. Is that a thought? But it is what it is. I got in before the wave, I guess. All right, so we need the volume of the solid formed by the intersection of the surfaces. All right, so it's a similar concept as the one previous to it. You know, very, very similar. I mean, it's pretty much the same. You know, there's always going to be a couple of twists and turns, but we have that little capsule in the middle that we have to find the volume contained within. All right, so the big challenge in pretty much all of these cases is always going to be identifying what your dominant function is and what the dominant and non-dominant one is, because when you're looking at a three-dimensional graph, sometimes it's hard to even get a sense of what the shape is, let alone which one is more dominant than the other. All right, so what I'm going to need is the intersection, because again I have that ring in the middle, so that somewhere they cross and they form some, could it be circular, maybe it's elliptical, I don't know, but there's going to be some sort of intersection that's going to be a two-dimensional trace. All right, so I'm going to set x squared plus y squared minus 3 equal to 3 minus x squared minus y squared. All right, and so combining terms, I'm going to add an x squared to both sides, a y squared to both sides, so I get 2x squared plus 2y squared. Add the 3 to both sides, I get 6. And so I'm looking at x squared plus y squared is equal to 3. All right, and so that's giving us a circular relationship. X squared plus y squared, circle with the center at the origin and a radius of 3. Radical 3, which tells me that my polar equivalent to that is r equals the square root of 3. All right, because all we need to do is identify what the radius is. This is what we talked about this last time. You know, you could replace the x squared plus y squared with an r squared, and then take the square root of both sides, or you could just jump right to this. All right, so what we have are our r bounds, because it may not seem this way, but, or at least from a two-dimensional rendering, but this is going 360 degrees around, and you can just draw a rough sketch of that, because if we're looking at the xy plane, that circular region that I highlighted on the graph, this guy right here, that would correspond to all of this. All right, so the base region, the quote-unquote base region, is going to go from 0 to 2 pi. All right, so that's a measure of theta. Theta equals 0, theta equals 2 pi. So now it's really just a matter of setting up my double integral so that I could find the volume contained between the two figures. All right? And so establishing dominance is going to be important. Well, it's always going to be important. So we have z equals x squared plus y squared minus 3. X squared plus y squared is r squared, so r squared minus 3 is our first function. All right, that's an upward-facing parabola. All right, so if we're looking at it strictly in terms of r, that would give us our upward-facing component. And the other piece would be z equals 3 minus, I'm going to cut the step here and just factor out the negative, z equals 3 minus x squared plus y squared in parentheses. So z equals 3 minus r squared. That would be our downward facing parabola. All right, but honestly, you don't even really need to know that. You would just want to say, all right, if r is equal to 0, what would z be? All right, so if you haven't gone outward on the xy plane at all, all right, so you're staying on the z-axis, where am I in terms of z? Well, for the first one, I'm 3 down, and for the second one, I'm 3 up. All right, so this one would have to, the second one would have to be the dominant function. All right, so this is my dominant function. All right, so when I'm setting up my double integral, I'm going to go from 0 to 2 pi. I'm going to go from 0 to root 3. And then I'm going to find dominant minus non-dominant. So 3 minus r squared minus r squared minus 3. That whole thing multiplied by r dr d theta. All right, so got rid of all the x's and y's and all that stuff. It's all in terms of r's and thetas, so we're ready to rock and roll here. Even better, my innermost function is in terms strictly of r. So this is calculator ready. So that's kind of a nice little characteristic here, because yeah, I could do the algebra pretty easily, but the key ingredient here is that I don't want to. All right, so 3 minus, well, double parens, really, I think. Yeah, because one for the integral and then one for the actual function. So 3 minus, we'll use x instead of r, x squared minus another x squared minus 3, close it up twice, pop an x on the outside, dx. You could use r's if you want, but I don't want to hit alpha and then another key when I could just hit one key. All right, and this is going to rad 3, 0 to rad 3. All right, just double check that you typed it in all correctly. Looks good. 4.5. All right, so that's a surprisingly clean answer. Maybe not surprisingly. I mean, I guess it's only surprisingly because we didn't do any of the algebra, so I didn't know what to expect. The rest you could do by hand, but you could also just not. The key challenge here is not actually integrating. It's just coming up with the integral that you need to integrate. All right, so we know that this is some multiple of pi. If you did it by hand, you'd see what it is. But we can go with the approximate value too. So 28.274 roughly. But if you want to divide out the pi and see what it really is, 9 pi. You know, if you get irrational, it's either going to be a multiple of pi, multiple of e, or some square root. The only time it gets kooky is if it's the square, it's like the sum of square roots or something like that. You know, you have like an irrational number that's pi plus the square root of 7. I mean, there's no like short calculator trick that's going to help you figure out that value just by knowing what the decimal is, right? I mean, unless you're really insightful about this kind of stuff. Because the best way to really kind of get good at this stuff is through experience. So I don't want to do too much of the thinking for you. You'll see some names here. Find the volume, like in number 5, inside the hyperboloid of one sheet. It's like, now we're just making up names for stuff. And that's really what it is. It's just that it's one continuous hyperboloid. It's connected, as opposed to a hyperboloid of two sheets, which is two separate graphs that together make one function, but you have to actually pick your, well, I was going to say pencil up off the paper, but really like your easel up. I don't know, your paintbrush up, because it's three-dimensional, so it's always definitely a work of art when you get done with it. But it's connected is really what that's saying. All right. So hyperboloid of one sheet, or the volume inside the hyperboloid of one sheet defined by the equation given. All right. So now it's a little bit of a different story, because you might look at this and say, wait a minute. There's only one equation here. We've been given two equations before, and now we don't have two equations. So what's going on here? So I want the volume inside this hyperboloid of one sheet. So we have the two opposing cones, so the inverted cones that come together to form a point. Each one forms like one of those like paper water cooler cups, the cone-shaped ones. I want the volume inside both of them. So, okay, I guess I could just find the volume inside one of them and double it. All right, so that part's not the challenging piece. The challenging part comes from the fact that when we find, using a double integral, when we find the volume, we're finding the volume underneath the surface. All right, not within the surface, but underneath it. All right, so between the surface and the xy plane. That's one of the benefits of knowing how to convert to spherical coordinates, because when you're finding the volume for spherical coordinates, you're finding the volume that's the deviation from the z-axis. All right, so that would be great for this, but we can't use that. All right, so what we need to do is figure out, and I'll just start marking it up because that's going to be really the only way to handle it. We're going to have to find the volume contained between the figure itself. Undo, because that was stupid. Volume contained between the figure and the xy plane. Let's get some kind of representative of the xy plane here. I guess that's good enough, because there's no way I'm going to be able to draw it three-dimensionally. Yeah. I mean, I guess I could do something like this and maybe try to figure something out on the other side, but I can get all of these volumes here and then add them up, and then take away from that the volume contained between the, well, I'll just say it, the cylinder, this topmost surface here. If we project it down upon the xy plane, it would create a cylinder. We could find the volume of that. So find the volume of a cylinder, and subtract from that the volume contained between the surface and the plane itself. I'm just trying to make it look a little bit more horizontal. Something like this. I could even give it a little bit of a bow. Yeah, I'm just making it look uglier and uglier by the second. All right, so we still need all the things that we needed before. All right, so the cylinder part's going to be easy. Okay, because all I would need is volume of a cylinder formula, pi r squared h. Right, so I just need the radius of that topmost, well, if it were a flat surface, that topmost circle. I need the radius of that. I have the height. It says it's going from -2 to 2, so I'll just go from 0 to 2. Right, because we're going to double it later on anyway. But I'm going to need this radius here. All right, so we'll start with that. So we have x squared plus y squared minus z squared is equal to 1. I'm going to let z equal 2. So that gives me x squared plus y squared minus 4 equals 1. So x squared plus y squared is equal to 5, which means r is equal to the square root of 5. All right, so I have my radius. So pi r squared h is the volume of the cylinder. So pi times square root of 5 squared times 2. So the whole cylinder is going to be 10 pi. 20 pi when we double it, but we're not there yet. All right? So at least we have that. Now what I have to do is figure out what the volume is going to be contained between that top level of the cone, because it's forming a cone-shaped figure, all of that volume that's contained between the outer surface of the cone and the xy plane. All right, so, well, we know what the function is, we just got to solve it for z. All right, so I'll go back to that. You got to attack this a bit at a time. Don't get overwhelmed with, like, I got to do this, I got to do that, I got to do that. What you do is you just do something. All right. Like the only line in Batman v Superman that was any good, you don't have to save everyone, just save one person. All right, that's all you're doing. Just do one thing correctly, and then after that, you'll be able to do another thing, and then another thing, and then before you know it, you'll have the solution. Because there's so many moving parts to all this stuff that you could find yourself overwhelmed if you're not careful. All right, so I'll do a little switcherooski here. X squared plus y squared minus 1 is equal to z squared. Now, I only care about the top half. Like I said, we're only going to focus on that because we'll just double everything later on. All right, so this is the top half. Little notes to yourself aren't the worst idea either. I suppose it's better than talking to yourself like I do. It's weird. I'm weird. All right. So we know our theta is going to go all the way around, so I'm not worried about that. It's the r. That's the r that I'm concerned with. All right. So you got to be thinking about how the r is going to behave in this situation. Now, it might be surprising to realize this, but we've already figured it out. We already know the shortest distance r is going to travel and the furthest distance r is going to travel. All right, we did it up here. When we plugged in the z value of 2, that told us the furthest extent of r, because that'll get us to the outer edge of the surface. The shortest distance it could travel would be 0, because that would put it right at the pole. That's where it comes to a point. Right, so we actually already have our bounds. All it takes is a little bit of thinking. So that's what I was saying, just do something. Just do something that you know is correct, because everything else is going to be kind of fleshed out in the process. All right, so I know that I'm going all the way around on this thing. So 0 to 2 pi. I mean, you could draw the two-dimensional, the XY trace of it, but really, I mean, it becomes extraneous, because I didn't even draw it on the last one, but the couple of problems that preceded it, all I was doing is drawing a circle just to label it 0 to 2 pi. All right, so we don't need that. We know that this is going from 0 to pi, 0 to root 5. And then all I'm not looking for the volume bounded between two surfaces, although I could, but I don't want to. I'm just finding the volume bounded between x squared plus y squared under a radical minus 1. Well, the x squared plus y squared under a radical, that's the same as saying r squared. All right. So, for the sake of not screwing this up in the final step, I'm going to write 10 pi minus that, and then in parentheses, I'm going to put a 2 in front of it. Oh, and also, don't be shocked if the question on the test just says simply, write an integral or set of integrals that could be used to find the volume for a particular situation, in which case you just stop right here. All right. But if it asks you to go to distance, you're kind of happy because even though you know that U substitution would be the appropriate approach for integrating this, to know that you don't have to do the U sub approach is kind of nice. All right. So go through the process. Math 9. Ah, you know what? I was gonna say I'll put the whole thing in there, but the calculator sometimes it handles double integrals and sometimes it goes absolutely ape you know what. Do you know what? I don't know. Because YouTube kids, I have to click it's not for them, so. Zero to root 5. Nan? Who do you think you are? Why would nan be an issue here? Oh yeah, the 0 would be an issue, but that would give you negative under the radical. Aha! Yeah, good call.
What is it?
Yeah, it's the 0 that's the issue, because if r is equal to 0, you get, if r is less than 1, you get a negative under the radical. Even if you integrate it, you'd still get a radical, so that would be a problem. All right, so slight adjustment. I would want to know where this function exists on the xy plane. So I'm going to let 0 equal the square root of r squared minus 1. Square both sides. All right, so these are the values that would give me 0. Anything in between these two values would be bad news. So therefore r has to be greater than or equal to 1. All right, so I have to make that slight adjustment. So that's just telling me that this doesn't actually come to a point, even though it appears to. It comes to a location when you get to the xy plane where it minimizes at the unit circle, which is weird because I thought it came to a point, but now that I think about it, it really can't. Because if it's going to be a three-dimensional surface, it has to have some thickness to it in order to still continue on and become the other function. Otherwise, it would be of two sheets. Right? Because if it came together at a single point, that single point would be dimensionless. Or at least it wouldn't be a three-dimensional rendering. It would only be two-dimensional at best. Right? So what's happening here, even though it doesn't appear that way, it's coming together kind of like I was going to say an hourglass, but maybe not so. Like even more extreme, But it minimizes at the unit circle on the xy plane. All right, so slight adjustment.
So if it said two sheets, that would be a point?
Yeah, or it would be a complete disconnect. All right, so slight adjustment. No nan, so that's good news. Math frac that. Math frac that. Oh, that's disgraceful. It can't math frac that. All right, whatever. Yeah, it's 2 2/3. So, yeah, it's not hard. It's just what, 8/3. So, 0 to 2 pi, 8/3 d theta, which is going to ultimately end up, like I said, just take, it's constant. So the difference between the bounds, which is just 2 pi, multiplied by the constant itself, 16 pi over 3. So, say it again? Yeah, we're going to do that too. So we're going to subtract that from 10 pi minus 16 pi over 3. And then double it. And all of this is under, under the assumption that you're interested in having a clean answer. You're perfectly allowed to not have a clean answer as per the rules of the course. So 2 times, well, it's 30 minus 16, so 14 pi over 3. So we're talking 28 pi over 3. I'll leave those for you to try, and then we will talk about triple integrals. Now, triple integrals are pretty easy in that, you don't necessarily realize that you've been using triple integrals all along. Even for finding single integrals, you could represent it with a triple integral. All right, double integrals, certainly you could represent it with a triple integral. All right, it's just very often ends up being an extraneous step that's unnecessary. All right, but really what we're trying to do here when you're finding a triple integral is you're finding little cubes that exist within a bounded region. All right, the volume of little cubes. So we have a dimension, and this length here would be dx. This one would be dy, and this one would be dz. So what you would end up having is infinitely many. So this is like a Riemann sum, in that you have infinitely many teensy tiny little cubes that are occupying this space in this direction. So we would integrate with respect to x. All right, so we have our dx. We would integrate all of those. All right. Then we would have each of these teensy tiny little distances in the direction of y. So each of these. Every one of those collectively, if you integrate them together, if you combine them all together, would give you the sum total in that direction. And then what you would have is all the teensy tiny little distances in the direction of z. So the vertical distance. And that would give you the triple integral of some function of x, y, z. So the natural question that you might have, because really what we're doing when we take all our z's, we have every one of those, that's just on one level. Honestly, we're going all the way up with this bad boy, but, it becomes kind of a waste of time. Like all of those cubes would be shooting on up the line here until it occupies the entire space. So we'd have one of these for each one of them, and so on. So we would occupy all of the space in each direction. All right, pretty crazy. That's a lot of space to occupy. But you might be wondering, wait a minute, didn't we just find volume? Didn't we just do that with a double integral? So why are we doing it with a triple integral? And the answer is, well, because we were using triple integrals, we were just skipping a step, all right? And I'll show you what that means in a sec, all right? So, well, I'll show you now, but it'll take a sec. So the first example, use a triple integral to find a volume between the surface defined by the function below, there's our function, and the region, so it's a rectangular region in the xy plane, which is fine, all right? So that means that we can swap our x and y bounds all we want. So we have a z function defined in terms of x and y, all right? But what we could do is define this function as f of x, y, z so I could write this as a function of f of x, y, z. I put my arrow the wrong way. Or I could write it as a function of x, y. It all depends on how I want to approach this thing, all right? But let's say we want to keep it simple and focus on writing it as a function of x, y, z, all right? And let's just say, I'm sorry, x, y. And let's just say that that function is unknown. What I would need is a triple integral It doesn't matter what the order of integration is because of Fubini's theorem. All right, if you're over a rectangular region, the order is interchangeable, and that's what's happening here. All right, so I can state that this is going from -1 to 1. This is also going from -1 to 1. All right, so at this point I can say, well, I have, well, what do I have? Some constant? Maybe. What I can do is I can just say that this is some function that we'll call 1. All right, whatever you want. It doesn't make a difference. But what we're going to do is integrate it over the interval of 0 to z. All right, so if I solve this for z, I'd have z equals 4 minus 2x plus y. All right, because really the bottom line is what I need to do is bound this function, and the dz, dy, dx is the function that gives me the volume in that bounded region, depending on what the end of the boundaries of integration are. All right, so the fact that I am multiplying these three things, oh, that looks terrible, undo. The fact that I'm multiplying these three things here actually gives me the volume, so infinitesimal volume. That's not how you spell infinitesimal. Crap. I don't think I've ever spelled it. I've always just said it. Infinitesimal, I think. Yeah. Yeah, it's a good thing I didn't have that word in the 4th grade spelling bee championship of Dutchess County. Otherwise, I wouldn't have won. So, volume. By integrating all of those infinitesimal volumes together, I'm getting the true volume bounded by these three boundaries of integration. All right. So, you could carry out the process and say, all right, the antiderivative of 1 with respect to z is z on the interval of 0 to z. Okay, so that's just z. And that's a general rule. So what this ends up being is equivalent to -1 to 1, -1 to 1, z, which in turn is equal to 4 minus 2x plus y, dy dz, dy dx. All right, so what we're actually doing here is we're actually applying the step prior to the double integral. Because the last problem, what we would do is we would just jump off of this. We would find the double integral for a particular z function, and then with the appropriate boundaries of integration, right, associated with the variables of integration, right? But by showing this additional step, all we're saying is that there is that one component where we're actually generating the z function in and of itself that allows us to apply the double integral concept. All right. So at this point, now you're just applying techniques for finding the solution to a double integral. So I'd be looking at, well, I just focus on this piece. Integrating with respect to y, we're looking at 4y minus 2xy plus 1/2 y squared over the interval of -1 to 1. I'm going to do a little plugging and chugging. All right, we're plugging in for y. So 4 minus 2x plus 1/2 minus -4 plus 2x minus 1/2. So 8 minus 4x, and then that would be plus 1. So 9 minus 4x. And so then it just becomes an ordinary integral. On the interval of -1 to 1, which you could pop in your calculator if you want. Nah, might as well. Undo. Less writing. So 9 minus 4x. I know it's linear, but it's been a long day. So 18. So it actually ends up being a pretty clean answer. So you might be wondering, like, okay, so could I have figured that out using another method, like maybe a geometric approach? This is the equation of a plane, and planes are usually pretty user-friendly, but the thing is we don't know what kind of plane it is. If it's parallel to the xy plane, in which case it's just a matter of length times width times height, but odds are it's some triangular looking plane, so it's on an angle, right? If that's the case, then you would have some length times width times height, but then you'd have that wedge part of it that you'd have to figure out, all right? So, yeah, it's pretty interesting. Now, it is possible that you could be taking a triple integral over a rectangular region or even a non-rectangular region, but that triple integral is going to give you something called density, all right? And that density in here is the same as density that we would be evaluating in physics class, all right? So it's basically taking the concept and expanding it into the fourth dimension, because the triple integral is finding, like you would think volume, but if you're talking about a fourth dimensional graph, you're talking about each different line or point having a texture to it, or a thickness, or a mass, or a density, all right? So it's really just, it's not a matter so much of occupying space, it's how the space is occupied. So when you get into the fourth dimension, you got to imagine, and this is where things kind of get crazy, because you really do have to imagine it. There's some apps out there that try to do a pretty good job of it, but like we have a space in here, like I could tell you what the volume of this space is, but at any different location in the space, the temperature is different, right? Maybe in a very minuscule sense, like maybe it's 72 degrees in one spot and like 71.98 degrees at some other spot. But there is varying temperature. There's variance within this volume. All right. Anytime something varies over a three-dimensional space, that puts it into the fourth dimension. All right. It's very commonplace that people represent the fourth dimension as time. That's a complete fallacy. That's not at all what it is. Right? You could represent time as a dimension, but that doesn't necessarily mean it is the fourth dimension. All right? Time could be the 10th dimension. It doesn't make a difference. It's just a dimension. It's not designated as the fourth dimension. Right? Because we have a whole lot of other dimensions to get through before you start thinking about what would be time. You know, like what would be the physical manifestation of time? Because we do have a physical manifestation of density of gases. You know, like it just like right out of an old Batman TV episode. You know, the air conditioner all of a sudden starts spewing out noxious gas. All right, so the way the gases are diffused within the environment, all right, that would be a new variable within this confined three-dimensional space. How that gas varies in this space is a new variable that puts us into the fourth dimension. All right, so how do you graph that? Well, not easily, right? Because we were already struggling, by we I mean me, you'll probably do a better job than I would, but graphing something in three dimensions is already a pain in the ass without technology. So imagine doing something with fourth dimensions. So like air currents within the three-dimensional graph. You could see it all the time on weather maps. You know, like the old school ones, like in elementary school, when you were learning about like jet streams and things like that. All it was like an arrow on a map, but that didn't tell you anything about like where that arrow was relative to the ground, what direction. You get a general sense of the direction, but we didn't get a sense of what the slight minor variations are. All right, so if in order to really represent the fourth dimension, you would have to plot every single particle that could exist in the domain of that three-dimensional space. All right, so if the idea or the word nightmare is coming to mind, then that's the correct word, because drawing that out is just terrible. All right, so if we start getting into things like volume, then the natural next dimension would be something like density, because that's one thing that we could do is we can evaluate the density over a confined space. All right, so we have rho equals m over v, right, m being mass and v being volume, so m is equal to rho times the volume. All right, so if we get a product of rho and the volume, then what we end up doing is creating a triple integral of some new function that density function multiplied by volume. So density so the product of density and volume gives us mass. So the triple integral of density and volume gives us, as a result, the combined mass over a space. All right, so this is equal to the combined mass over a space. And honestly, the only real way to accurately and effectively graph in the fourth dimension would be by using, by hand, would be by using different colors. So areas with the highest mass, you would make that the darkest colors, and the lowest mass you'd make with the the lightest colors. But density. But the issue is you have three different directions to be working with. So how do you do that if it's not uniform in terms of the density down a particular line? All right, so I have a plane here. If the density varies, so I'm looking at a cross section of that plane. If the density varies down that plane, from this perspective, I wouldn't be able to see it. So now I have to ever so slightly shift my perspective so that it's on a little bit of a slant, so that I can give it texture all the way down the line. All right, and what if it varies from bottom to top? All right, so density in terms of fluids, for example. You know, if it's not uniform density throughout the fluid, you know, oil and water, right? You take a little Italian dressing, you know, you buy it at the supermarket, it's all right, it's divided, right? But then you shake it up, now it's all mixed, but it's gonna start separating itself over time, right? So that movement is variable, but the density of the liquids and how they push off of one another, it can be represented with a fourth dimensional graph, all right? Not easily, all right? But that's the beginnings of that kind. Number two, just telling us to find the triple integral. It's giving us the function, and it's the same idea for the one below, except here it's bounded in a different way. Here we're dealing with rectangular bounding, right? Whether it's in X or Y or Z, they're constants that represent the bounding of the region. So, you know, we're in pretty good shape because all we would have to do for this one, so this one is as easy as it gets. Create our triple integral of 4y e to the x sine of z, and do that in the order that we find to be the most convenient. All right. So the question becomes, well, is it hard to do it in any way? Right? Because we're holding whatever variable that we're not interested in as constant, so, or variables in this case. So it really doesn't make a difference. So I'll take care of the z first, because really the hardest part of this is the trig, and that's not even that hard. That's going from 0 to pi. So we'll tackle that first. All right, so the antiderivative of sine is negative cosine, so we're looking at negative 4y e to the x cosine of z on the interval of 0 to pi. All right, if I plug in either a pi or a 0 for cosine, we're going to get something non-zero out of it, so a little bit more. So negative 4y e to the x cosine of pi is negative 1, so that makes this positive, minus negative 4y e to the x cosine of 0 is 1. So two negatives give me a positive here. I'm looking at 8y e to the x. All right. So then it's at this point, because I'm dealing with rectangular values, right? These are not function based. Right? These are based on constants. That's how I know that I'm able to do what I'm about to do. I look at my integral here, and I say, or my antiderivative, and I say, okay, which one do I want to do next? It really doesn't matter. I might as well tackle the e. All right, so that means that I would be doing the dx part of it next. So that puts it on the interval of 0 to 1. All right, so my next step in the process, let me get rid of that. Next step in the process would be to set up an integral going from 0 to 1 of 8. You want to cooperate there for a second. 8y e to the x dx. We're holding 8y constant. Fortunately, the antiderivative of e to the x is e to the x. So this just becomes 8y e to the x over the interval of 0 to 1. All right, so that becomes 8y e to the x minus 8y e to the 0th. E to the 0th is 1, so 8y. All right. So that leaves, last but not least, integrating with respect to y. And you could have done it in any of the different ways. You could have done it z, then y, then x, z, then x, then y, x, then y, then z. So was that 6 permutations? So any of 6 possible ways, and you would get the same answer. This is going from -2 to 2. So I set up my integral here, going from -2 to 2, this time of dy. All right, so 4y squared e to the x minus 4y squared on the interval of -2 to 2. All right. Oh, did I say e to the x? E to the first, I mean. Sorry. Oh, now I'm locked out for editing. Got to use the whiteout. E to the first in both cases. Still an e there, but not an e to the x, because we're not going to get an answer in terms of x because we're substituting in for each of the values. All right. So pop in the 2. So we're going to get 4 times 4, so 16e minus 4 times 4 is 16 minus 4 times 4e, so 16e minus 4 times 4, so -16. And after all of that, you get a nice, crisp, clean 0. Good for one of those every once and again. Right? And all that means is that we have equal parts above the xy plane and below the xy plane. It's they cancel each other out. You have negative volumes and positive volumes, just like you could have negative areas and positive areas. All right, so the next one, evaluate the triple integral over a solid tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. That's a little bit of a different story. All right, so we have our multivariable function. We know that we're coming up with a triple integral. Of 5x minus 3y. It's just a question of, okay, so cool, what's going in there? Well, we have some relationships that we could work off of here. We know that it's bounded by the planes x equals 0, y equals 0, z equals 0. All right, so x equals 0. You're talking about the x equals 0 plane, you're talking about the yz plane. Y equals 0 is the xz plane, and z equals 0 is the xy plane. Right? But we also have this relationship that's the upper, or it's the ceiling of the bounding. That we could express as a z function in terms of x and y. All right, so z in terms of x and y would be 1 minus x minus y. All right, because if we're bounding it in terms of z, we need to know where we're starting and where we're stopping. So the lowest possible value for z would be 0, and the highest possible value of z would be this relation 1 minus x minus y. So we would be going from 0 to 1 minus x minus y. All right. So then we just need expressions that would represent y equals 0 and x equals 0. All right. So we just want to think about the furthest that we can go out on the x-axis and the furthest that we can go out on the y-axis. All right. So if x equals 0, we would just look at that function. 0 plus y plus z would be equal to 1. Now I have a relationship between just y and z. All right, because I know y has to be going from 0 to something. It's just a question of 0 to what. All right, so when I integrate with respect to z, all right, I have a z equation here. Z equals 1 minus x minus y. That's what this is. This is my z. Z equals 0 to z equals this. When I integrate, I'm going to get something in terms of x and y. All right, because I'll get an answer that has a z in it, but then I'm going to sub those values in. And so I'll be looking to integrate with respect to y. So what I need now is a y equation that's in terms of well, I'm sorry, a y equation that's in terms of x. So what I want to do, I miswrote, misspoke, miss everything. I'll just leave it here. This is a true sentence. But what I want to have here is a relationship between x and y. So we're going to let z equal 0, and that would give us x plus y plus 0 equals 1. And you know, while I'm at it, I'll do the other one. Just so it makes it seem like I did all this on purpose. Let y equal 0, and you get x plus 0 plus z equals 1. I have a relationship between 2 out of the 3 variables. All right. So the relationship that I would have here for the blue one would be that y is equal to 1 minus x. All right. So I'm going from 0 to 1 minus x. All right, and so that's an equation for y, or both of them are equations for y in terms of x. So let me get purple, get back into play here. I'll just write equals y, just kind of chuck it in there. And so that's that one. Now I just need a dx. So I'm just manufacturing this as I go. I would want to know how x is bounded. All right, so we would just need to come up with numerical values that represent the location of x. So if we're dealing with that, we would have to be in a situation where x exists as some numerical value, but y is equal to 0 and z is equal to 0. All right. So out of all these possibilities, this one, the green one, ends up being the one that's useful for finding the bounds for x. All right, because I would replace the z value. I already replaced the y with 0. X plus 0 equals 1, which means that x would go out to 1. So this value here is a 1. Now you can figure out this value is also a 1 by doing the same thing. And you can figure out that this value is a 1 by doing the same thing, replacing the x and y with zeros. And so you know that the outer boundary for x would be simply numerical. And you would get, and I'll just clean up the integral a little bit, 0 to 1, 0 to 1 minus x, and then 0 to 1 minus x minus y of 5x minus 3y dz, dy, dx. All right. This one is actually a legacy typo. And what I mean by that is I have pointed this typo out for a few semesters and nobody's ever claimed it, so I've never made the change. This one should be write an integral or a set of integrals that can be used to find all that stuff, right? So this should be the answer because it's a pain. I mean, it's doable, but it's a pain to actually go through the integration process. So if somebody wants that typo, of course, people don't take me up on my typos as often as I would. More money. All right, so this part, it's really just 2 minutes because here is how you convert back and forth between polar and spherical coordinates. That is all. I mean, they're not really, but it really is just another set of rules that you need to access. All right, but what I wanted to really talk about is this part, right? The diagram, because that really tells you what it is that you're getting when you convert to spherical coordinates, right? So what you're getting are 2 angles and a radius. All right, so that rho value is the distance from 0, 0, 0. The theta is the angle from the x-axis, and the phi is the angle from the z-axis. So you might look at this and say, well, that's great. How on earth is that going to be easier to manage than rectangular or cylindrical coordinates? Well, if your graph is spherical in nature, then it's very easy, because I can tell you right now that I can write the equation of a sphere as a constant now, right? Because really a sphere is equidistant from its center. So if I tell you that a sphere has a radius of 2, then rho is equal to 2. And that's your equation, because it doesn't matter what the angles are from the x-axis. It's going to go all the way around. And then from the z-axis, it's going to go all the way down and around. So your theta and your phi values are going to be on the interval of 0 to 2 pi in both cases. Right? So what you're going to actually do is sweep through an entire sphere just by knowing what the rho value is. Right? Because everything else will be generally infinite. Right? So really, at this point, your only job is to learn how to convert back and forth between the two forms. So those formulas up there are really important, but also kind of a sneaky little formula in here is we know that r is equal to square root of x squared plus y squared. That's the cylindrical coordinate system. We also know that r is equal to rho times the sine of phi just by manipulating some of these formulas here. So what we get is a consequence, and this is a nifty little substitution. So don't let this one get away, because oftentimes people get bogged down in the conversion from rectangular to spherical coordinates because they have to stop off at cylindrical coordinates and say, okay, so square root of x squared plus y squared is, all right, well that's equal to r. So how does r relate to spherical coordinates?
So rho sine phi is just the square root of r?
It's equal to the square root of r, exactly. Right, so, oh no, sorry, it's equal to r, because r squared is equal to x squared plus y squared. So it's this relationship. But this is the one that you want. That's going to make conversions a whole lot easier. So put a star on that. I mean, there's a reason why I highlighted it, but it doesn't come out well in photocopies.